Hello. In this video, we're going to continue solving trig equations. And just to start, we're going to do one more without a calculator. So here we have -1 plus 3 sine theta equals 1.649. So again, we want to isolate this trig ratio here. And the first thing we should do is probably add 1 to both sides. So if we do that, we get 3 sine theta equals 2.649. Next up, we got to divide by 3, and that means we're going to have to do a little long division over here because we're working without a calculator. 2.649 divided by 3. 3 doesn't go into 2, but 3 will go into 26. 8 times. That'll be 24. Bring down the 4, 3 goes into 24 8 times, 24. Bring down the 9, 3 goes into 9 3 times. Oh, this is looking nice. We're going to have no remainder, so we have sine theta equals 0.883. Now, when we go to look that up in the trig table, it actually looks super close. It's almost exactly the entry with 62 degrees. So that's exciting, 62 degrees. And using our cast rule, we're going to expect sine in quadrant 1 and quadrant 2. So the first theta is actually ready to go. The second theta, we have to do 180 minus theta, or reference angle, I should say, theta r. And that's going to give us 118 degrees. So these are our two answers, and we have solved the question. But, I mean, it would be nice if we had a more precise solution. I mean, 62 degrees is nice, but what if we were building, say, a bridge? Is 62 degrees enough, or do we need more precision? I mean, you could certainly imagine if you were landing on the moon, or if you were traveling to Mars, if you were making some life-saving medication, going to a whole number certainly doesn't sound like enough precision. You might need 1 decimal place, 2 decimal places. And of course, we know in pre-cal, we always want 3 decimal places. So how are we going to get that kind of precision? How are we going to get 3 decimal places? Is it exactly 62.000 degrees? Or is it like 001 or 005? Maybe, we don't know. We don't know what the decimal place is. In fact, we don't know what any of these decimal places are. We only know it's close to 62 and it's not 63, because our trig table only goes up by whole degrees. It goes 61, then 62, then 63, but it doesn't help us in between. Now, believe it or not, there were actually giant trig tables that people made that went to 1 decimal place or 2 decimal places or even 3 decimal places to get that level of precision that was needed for things like electronics or space travel or medications or, really big feats of engineering and construction. But thankfully today we don't have to dive into some dusty textbook. We have our calculators. And so we are going to do the problem again, and we're going to get the angles to 3 decimal places. So our initial question was -1 plus 3 sine theta equals 1.649. And we can get, initially the same steps are the same. We can do 3 sine theta equals 2.649. We divide by 3 on your calculator. When you divide by 3, because we had an exact value, you should still get the same number, 0.883. All right, so now we get to use the sine inverse button. So sine -1 or sine inverse of 0.883. And let me just check it here on my calculator. If you type that in, you should get 62, that's a good start, 0.00639666. So we actually get it to, wow, it looks like we have 7 decimal places here. But we don't actually need all of these ones. We only need it to 3 decimal places. And of course, the 3 here rounds down, so it doesn't affect our answer. So we would have 62.006 degrees. And then we do 180 minus 62.006. And that's going to give us 117.994 degrees. So these are our two answers. Now again, you might say, well, Mr. Peters, if I'm just designing something for my art class, I don't think I need that third decimal point. And I would agree. I think for many things, just going to a whole number is fine. But in pre-cal, we need those 3 decimal places. And imagine you're sending people to Mars, right? We need a high level of precision. You wouldn't want to be off by even 1 place in the third decimal because, I mean, you'd probably miss Mars, and that would be a bit of a bummer. So let's go ahead and do this again. This time we're going to do it in radians. So what does that mean? We start off with sine theta equal to 0.883, just like before. And we even get to do the same sine inverse of 0.883 in our calculators. So we're going to get the 62.006 degrees. And of course, the other one, 117.994 degrees. But we're now going to take those angles and we're going to convert them into radians. Now, what that means, if you remember, if you have something in degrees, the way you convert to rad is as follows. You take your angle, you multiply it by pi, and you divide by 180. So let's go ahead and take 62.006, multiply by pi, and divide by 180. Go ahead and type that in on your calculator. Make sure you're using that pi button and hit equals. And you should get 1.082 rad. Now for the other angle, if you remember, the way we got the 117 was we did 180 minus our reference angle. So we'll do the same thing over here, except 180 in degrees is now pi in radians. So 180 minus our pi minus our reference angle. So hit pi minus 1.082, and you should get 2.0595. That 5 makes the 9 round up, and then the 9 rounds up to a 60. So you should get 2.060 rad. And so these would be our two answers here. We'd have 1.082 and 2.060. Unfortunately, the second answer is actually wrong. And I want to show you how we know it's wrong. Let's take this angle here, and let's try to convert it into rads. So instead of doing the whole reference angle business, let's just take our other answer and convert it into rads. So remember, we multiply by pi, divide by 180. So let's try that. 117.994 multiply by pi and divide by 180. That's going to give us 2.0593, and the 3 rounds down, so 2.059 rad. So now we have 2.059 and 2.060. Again, some of you might say, Mr. Peters, we're only off by 1 place in that third decimal. 0.059, 0.060, that doesn't feel like a big difference. But again, 1 in 1,000th, if we're talking about manufacturing a computer chip or going to Mars, these differences matter. And ultimately, even if you don't believe me, the differences do matter on the pre-cal exam, because if it's not perfectly correct to 3 decimal places, you don't get full marks. But why? Why did that happen? Why did one method give us one answer and one method give us the other answer? And why am I claiming the second one is correct? Well, the problem is this step right here. We have 1.082, but actually there's more decimals behind it. I mean, really, in fact, the problem was actually up here because we had 62.006 and there were more decimals after that. What we want to do is anytime we have a final answer, we want it around to 3 decimal places. But if we're using the answer in another calculation, So if you notice right here, we're using this number in a calculation. We need to have all the other decimal places after that number on our calculator so we carry the precision with us until the very end. Similarly here, if you notice, we do pi minus our reference angle. So our reference angle should have all the extra decimals with it. We shouldn't just be using the 1.082. If we carry those decimals with us and then round at the end, then we'll get the correct answer. But if we round off too early, unfortunately, we get it incorrect. So if you want to see how to do this actually to get the correct answer, we would have to do something like this. So first we would do sine inverse of 62.006, or sorry, sine inverse of 0.883. And that's going to give us 62.0063966. And we leave the full answer on our calculator. Then we multiply by pi and divide by 180. That's going to give us 1.082215778. Then we take that answer and we do pi minus ans. You can use the answer button on your calculator to bring all the decimals with you. So pi minus ans. And that's going to give you 2.059376876. Then we simply round to 3 decimal places. The 3 rounds down. And so we're good. Again, we need to be able to do this question with the full level of precision. And what that means is keeping all the decimal places, either by typing them in manually or using this answer button on your calculator, until we get to the very end. Now there's actually another way of doing it, which is kind of nice. Rather than doing all this conversion, we can actually just do the question in radians, believe it or not. So if you have your calculator and the Mr. Peters recommended calculator, notice there's a little D at the top. That means that your calculator is set to, you guessed it, degrees. And we're able to convert it into radians. Now this will be slightly different for your calculator if you don't have the approved calculator, but if you just Google your calculator's name and how to change into radians, you should be able to figure it out. On this calculator, we need to select the setup option. And to do that, we hit Shift and then this button right here. So we go Shift and then we do the mode setup button. Mode/setup. And then we notice there's an option that says deg, that's degrees. And we notice there's an option that says rad, that's for radians. So if you want to go to degree mode, you hit 3. If you want to go to rad, you hit 4. So we'll go ahead and hit that one. And the little D here should change to an R. That means you're in radians. So now we can go back to the beginning of our question. Sine theta equals 0.883. We can do sine inverse of 0.883. And on our calculator, when we do sine inverse of 0.883, we will get 1.082 and so on, which is our radian measure. No need to multiply by pi and divide by 180. We have it in rad already. Then to get our other answer, again, remember using the cast rule over here, it's going to be pi minus our reference angle. So we just do pi minus ans, that pulls the answer right away. And so when we do pi minus answer, we should get 2.059 rad. And there are our 2 answers right away, and we didn't have to do any converting. All right, so let's try another one. We have 2 minus 1/4 sine theta equals 2.2. We want to solve it in both degrees and radians. So go ahead and pause the video and give this a try. At least solve it in degree mode. Make sure you put your calculator back into degrees, and then also try to solve it in radian mode. All right, so assuming you gave it a try, we're going to go ahead and subtract 2 from both sides. Negative 1/4 sine theta equals 0.2. We'll clear that 4, so negative sine theta equals 0.8. Clear that negative sign, so sine equals negative 0.8. Then we'll do our sine inverse. So we'll do sine inverse of, I'm going to drop the negative sign. Remember, this is the same as before. So sine inverse of 0.8. It's going to give you 53.130 and so on. This is your reference angle. Using the cast rule, we know that sine is going to be negative down here and here. This one is going to be 180 plus my reference angle. This is 360 minus my reference angle. So I'm going to get 180 plus my answer, which is 233.130 degrees. I'll also do 360 minus answer, and that will give me, well, actually technically we can't use the answer key again on our calculator. We have to go back and draw up that reference angle. So we do sine inverse of 0.8 again, then we do 360 minus answer, and that should give us 306.870 degrees. So here's my one answer and my second answer. And if we were to do this question in radians, well, it would be the same method. Everything would be the same up until here. But at this step, we would have to set our calculator into rad. And so when we do sine inverse of 0.8, well, it's going to give you definitely a different number because we're talking in radians instead of degrees. My calculator says 0.927. Then instead of 180 plus answer, we do pi plus answer. So pi plus answer should give you 4.0688. So round that to a 9 rad. And then we do 2 pi minus answer. Again, we have to grab that answer from our calculator again. So you have to do the sine inverse step again. But if we do the 2 pi minus our answer, we'll get 5.356 rad. And those are our two answers. All right. So again, I encourage you to pause the video, give this one a try, see what you come up with for your values. All right, so we take that -2 and add it to both sides. It's going to give me -5 equals -6 cos theta. Divide by -6. Cos theta equals 5/6. Now be careful here. 5/6 will be a decimal on our calculator. 0.8333 repeating, and we all know how tricky decimals can be with the rounding business. So just leave it as a fraction. It's going to be easier. So we're going to do cos inverse of 5/6. Okay, please don't round that or anything. Just leave it as a proper fraction, and it'll just be better for your calculator. Now that should give you 33.557. Let's just check our cast rule here. We're looking for cos to be positive. So I'm thinking quadrant 1 and 4. So this first one is actually one of my answers, 33.557. That's exciting. Then I'll do 360 minus my reference angle. On my calculator, I do 360 minus answer. And that will give me 326.443 degrees. If we do it in radians, it'll be the same up into that cos inverse step. But from there, when we do cos inverse of 5/6, we should get, let me just double check on my calculator. Cos inverse of 5/6 should get 0.586 rad. 2 pi minus reference angle for the other one. 5.697 rad for the second point. And those should be our two angles. Now for fun, we could do one that even has something a little wild. This one's got a tan in it, but again, the steps should be the same. Go ahead and isolate for it, use your calculator and solve it in degrees and radians. All right, so let's move that 3 over. Minus 3 tan theta equals 2. Divide by -3. Tan theta equals -2/3. Remember, it's good to drop that negative sign when you do the tan inverse. So you just do tan of 2/3. Again, this is not a nice decimal, so please leave it as a fraction. Tan inverse of 2/3 should give you 33.690. Based on our cast rule, we're looking for negative, so we're thinking quadrant 2 and 4. So the first one will be 180 minus reference angle. So 180 minus answer. That should give 146.310. And then 360 minus reference angle. $326.310. If you do it over here in radians, I'll just skip the steps, but you should end up with theta equals 2.554 and 5.695. Now we'll take some notes on this. What we're doing is solving basic trig equations. And the steps are the same as before we had a calculator. So you isolate the trig ratio. Then in this case, you use sine inverse or cos inverse or tan inverse on your calculator. Remember, we like to drop the negative. Makes it a little bit easier. Then you use your reference angle with the cast rule to find usually the two solutions. There could be only one solution, or as we go on, there could be more solutions when we look outside of 0 to 360, but that's like a usual good rule of thumb for these. So for an example here, why don't you try 7 cos theta equals -2, and just solve it in rad. You don't have to solve it in degrees. All right, just when you check your work, you should have the following. Theta equals 1.861 rad and 4.423 rad. Those will be, of course, in quadrants 2 and 3. Remember, in quadrant 2, do pi minus your reference angle. Quadrant 3 is pi plus your reference angle. Now over here for your example that you choose. We are working on Unit 6, Worksheet 5. And then you can write down any things to remember. The one thing that you should remember is always use all decimals until the end. There's a common mistake in pre-cal is that people will round early and then keep using that number throughout the rest of their question. It happens here and in other parts of pre-cal. And the key is that when you're working with your calculator, you want to use all the decimals available on your calculator until the very end. You do need to round to 3 decimal places, of course, but we only round our final answer. We don't want to round earlier in our work, and we don't want to use any of those rounded answers to calculate anything else. All right, hopefully you enjoyed this video, and as always, thanks for watching.